In this video, I'd like to begin the final section of Chapter 3 on counting atoms. And our goal is, if I give you a certain quantity of an element, you tell me how many atoms of that element are in it. But before we get to that, we need to talk about a couple of other things. Here's a question. What part or parts of Dalton's atomic theory do we now know are not correct? Think about it for a minute. Well, the first part is that all matter is made of atoms. That's actually not true. We saw earlier in the unit that the cathode ray is made up of electrons. Electrons are matter, but they are not atoms. So that part is incorrect, but Dalton didn't know about electrons. Another part that's not correct is that atoms can't be created or destroyed. We now know that in nuclear processes like fission and fusion, atoms can be created and destroyed, but Dalton didn't know about that either. The final part that we know is incorrect is that all atoms of an element are identical. Wait, what? You can have two atoms of the same element that are not identical to each other? Yes, because Dalton didn't know about isotopes. Isotopes are defined as atoms of the same element that have different masses. So the question is, why do they have different masses? Well, if they're atoms of the same element, they must have the same number of protons, but there's another particle in the nucleus that contributes to the mass of the atom, that is the neutron. So isotopes are atoms of the same element that have different masses because they have different numbers of neutrons. So let's talk about how we're going to describe a nuclide. The word nuclide simply means a specific isotope of an element that has a defined number of protons and neutrons. Let's take an example. A given nuclide has an atomic number of 35 and 45 neutrons in its nucleus. Describe this isotope using a nuclear symbol and a hyphen notation. Well, we know that the atomic number is the number of protons, which is 35. And we know that the mass number is the sum of the protons plus neutrons. So I'll add those together to get a mass number of 80. For the nuclear symbol, I will begin by writing the symbol of the element. How do I know the element? Well, if I know its atomic number, I simply find it on the periodic table, and I see that element 35 is bromine, so I'll write the symbol of bromine. In the lower left, I write the atomic number, 35, and in the upper right, I write the mass number, the total number of protons and neutrons, which is 80. So that would be the nuclear symbol for this particular isotope. The hyphen notation is simply the name of the element followed by a hyphen followed by the mass number. So I would call this isotope bromine 80. Let's do another problem. Write the nuclear symbol for iodine 127. So here I give you the identity of the isotope in hyphen notation, and state the number of protons and neutrons in the nucleus. Well, the nuclear symbol is going to be easy. I'll simply start by writing the symbol of the element. I'm told that this isotope of iodine is iodine 127. 127 is the mass number, so that goes in the upper left. And in the lower left, I write the atomic number of iodine, which I find on the periodic table as 53. So there is the nuclear symbol. Now, to determine the number of protons and neutrons, I simply need to do a little bit of subtraction. Okay? I know that I've got 53 protons, and I know that the mass number is 127. So to figure out the number of neutrons, I will simply take the mass number, subtract the number of protons, and that gives me 74 neutrons. Now let's talk about atomic mass. What does the term atomic mass mean? The atomic mass is simply the mass of one atom of a given isotope, and it is measured using a technique called mass spectrometry, which I won't go into, other than to tell you that it's extremely accurate and extremely precise. For example, one atom of oxygen-16 has a mass of 2.657 times 10 to the negative 23rd grams. Now, that's a really tiny amount because we're dealing with one atom, and using numbers in scientific notation, particularly when they're very small powers of 10, can be inconvenient. So scientists decided to come up with a new atomic mass unit called the relative atomic mass, measured in what are called unified atomic mass units, symbolized as U. And the U was defined as 1/12 the mass of one atom of carbon-12. Or, in other words, one atom of carbon-12 has a unified atomic mass of exactly 12 U. That's a definition. So let's look at some examples of relative atomic masses. Oxygen-16, the isotope of oxygen that has 8 protons and 8 neutrons, has a mass of 15.994915 U. Look at that. What is that, like 8 significant figures? That's crazy. Magnesium-24 has a relative atomic mass of 23.985042 U. Proton and neutron have atomic masses that are given there, slightly more than 1 U. Now, you see something interesting here. The relative atomic mass, measured in U, is very close numerically to the mass number. The relative atomic mass of oxygen-16 is very close to 16. That of magnesium-24 is very close to 24. But there's something strange about these numbers. If one atom of oxygen-16 is made up of 16 particles, each of which has a mass that is slightly more than 1 U, how can the total mass be less than 16? Well, it turns out that if I were to take 8 protons and 8 neutrons, squish them together to make one atom of oxygen-16, I would actually lose some mass. Mass would be destroyed. You know what happens to it? It gets converted into the energy needed to hold those particles together. What's the relationship between mass and energy? You guessed it. E equals mc squared. We will not be using that equation this year, and I just wanted to point out that interesting fact. Now, here is a question that's going to come up. I'm probably going to ask you this on an assessment. Explain the difference between the mass number and relative atomic mass of the given nuclide, and explain why they are always very close in magnitude. It's important to understand the distinction. The mass number is the total number of particles, protons and neutrons in the nucleus, and it is a counting number. The atomic mass is the actual mass of the atom measured in U, unified atomic mass units, which is a measurement. They're close in magnitude because each particle in the nucleus, that is each proton and neutron, has a mass very close to 1 U. Therefore, the relative atomic mass will be very close to the mass number. Now, let's talk about the atomic masses of elements that occur naturally. Copper occurs as a mixture of 2 isotopes. Copper-63 has an atomic mass there of 62.929601, very close to 63 as we would predict. And copper-65, the other naturally occurring isotope, has a relative atomic mass of 64.9277794 U. But if I look up the number on the periodic table in the bottom of the box, what I see is 63.546, which is neither of those two. And it's not halfway between 63 and 65 either. It's a little bit closer to 63 than 65. Well, it turns out that copper, these 2 isotopes, occur in different amounts. Of the copper that I dig up in the ground, 69.151% of it is copper-63, the lighter isotope, and 30.849% of it is copper-65, the heavier isotope. This makes sense because more of naturally occurring copper is copper-63 than 65. We would expect the average atomic mass to be closer to 63, and it is. But the question is, unit on that, the question is, how would we actually calculate that? Well, it's a pretty straightforward process. Here is how we calculate the average atomic mass of an element, not by simply adding the masses of the 2 naturally occurring isotopes together and dividing by 2. That would only be correct if it were a 50-50 mixture of the 2 isotopes. In this case, it's not, so we have to calculate what is referred to as a weighted average. And here's how we do it. For each isotope, you multiply its given atomic mass by its fractional abundance, the percentage abundance divided by 100. Add up the result for each isotope, and the sum is the average atomic mass. Let's do this for copper. So I take the relative atomic mass of copper-63, multiply by I take the fractional abundance of copper-63, multiply by its relative atomic mass, I get a value. I take the relative abundance of copper-65, expressed as a fraction, multiply by its atomic mass, and I get 2 numbers. The first term is the contribution of copper-63 to the overall average. The second term is the contribution of copper-65. I add them together, and I get 63.546 U, which is the value you see in the bottom of the box in the periodic table. So, to reiterate, the number you find on the periodic table is the weighted average atomic mass of all of the naturally occurring isotopes of that particular element, and this is how you calculate it. In our next video, we'll move on to actually counting atoms.